What if I told you that if you could travel faster than light, you wouldn't just break the speed limit of the universe, you would literally break time itself? And here's what will blow your mind. According to Einstein's equations, traveling faster than light doesn't just make you go backwards in time. It makes you arrive at your destination before you even left. Picture this. You're sitting in your room right now, watching this video. But somewhere in the universe, there's a version of you that traveled faster than light to get here. And that version of you arrived yesterday, before you even clicked play. In fact, that version of you could theoretically meet the you from today and have a conversation about this very video that hasn't happened yet. This isn't science fiction. This is what the mathematics of relativity actually predicts would happen if faster-than-light travel were possible. And the implications are so mind-bending that they challenge everything we think we know about cause and effect, free will, and the very nature of reality itself. Before we dive deeper into this rabbit hole that makes Alice in Wonderland look like a children's book, smash that like button if you're ready to have your understanding of the universe completely turned upside down. Subscribe and ring the notification bell, because we're about to embark on a journey that will literally change how you see reality. And let me know in the comments, what country are you watching from? And what time is it there right now? Because by the end of this video, you'll understand why that question might be more complex than you think. To understand why faster-than-light travel breaks reality, we need to start with Albert Einstein and the year 1905, what physicists call the miracle year. Einstein was just 26 years old, working as a patent clerk in Switzerland, when he published a paper that would revolutionize our understanding of space and time forever. Think of it like this. Imagine you're driving on a highway, and there's an absolute speed limit not set by traffic laws, but by the laws of physics themselves. This speed limit is 299,792,458 meters per second, the speed of light. But here's where it gets weird. Unlike a car that needs more and more fuel to go faster, light doesn't need fuel at all. It just goes at this exact speed, always in every direction, no matter what. Einstein discovered this through a thought experiment. He imagined riding alongside a beam of light and asked, "What would I see?" According to the physics of his time, he should see a stationary wave of light frozen in space. But this created a paradox: light waves can't be stationary. This simple question led to the most profound discovery in human history. Space and time are not separate things, but part of a single fabric called space-time. Here's what will blow your mind. Einstein realized that the speed of light isn't just fast, it's the cosmic speed limit, because it's actually the speed of causality itself. It's the maximum speed at which cause and effect can propagate through the universe. When you flip a light switch, the effect doesn't travel instant the bulb. It travels at the speed of light through the electrical field. Einstein's equations revealed something even more shocking. As you approach the speed of light, time itself begins to slow down relative to the rest of the universe. This isn't just theory, we've measured it. Muons are particles created in our atmosphere by cosmic rays. They have a lifespan of only 2.2 microseconds, which means they should decay long before reaching Earth's surface. But because they're traveling at nearly the speed of light, time dilation allows them to survive long enough to reach our detectors. GPS satellites orbiting Earth experience this too. They're moving fast enough that their clocks run slightly slower than clocks on Earth, about 38 microseconds per day slower. If we didn't account for this time dilation, GPS would be off by several miles within just one day. But here's the kicker. As you get closer and closer to the speed of light, something incredible happens to your mass. Einstein's famous equation E equals mc has a lesser-known cousin. As your velocity increases, your relativistic mass increases too. At 90% the speed of light, your mass doubles. At 99%, it increases by a factor of 7. At 99.9%, it's more than 22. Times your rest mass dot, this creates what physicists call the light barrier. To accelerate any object with mass to the speed of light would require infinite energy, literally impossible. It's not just a practical limitation. It's a fundamental law of the universe. The equations predict that reaching light speed would make your mass infinite, which would create infinite gravity, which would collapse the universe into a black hole dot. So when science fiction shows spaceships casually breaking the light barrier, they're not just bending the rules, they're proposing something that our current understanding of physics says is absolutely impossible. But what if there were loopholes? What if the universe has backdoors that Einstein didn't know about? That's where our story gets really interesting, and it's about to challenge everything we just learned. What if I told you that there might already be particles in our universe that are born traveling faster than light, and these particles experience time in a way that would make your head spin? Meet the tachyon, a hypothetical particle that exists in a realm where faster than light travel isn't just possible, it's mandatory. The tachyon was first proposed in 1962 by physicist Gerald Feinberg. At Columbia University, Feinberg asked a simple but profound question. What if Einstein's equations apply to particles that are already traveling faster than light? The mathematics revealed something incredible. Just as normal matter can't be accelerated to light speed, tachyons can't be slowed down to light speed. They're trapped in the faster than light realm, just as we're trapped in the slower than light realm. Think of it like this. Imagine two separate highways running parallel to each other, with an impenetrable barrier between them. On one highway, all the cars are forced to drive slower than 60 miles per hour and can never reach that speed. On the other highway, all the cars are forced to drive faster than 60 miles per hour and can never slow down to that speed. That barrier at 60 miles per hour is like the speed of light. It separates two completely different realms of existence. But here's where it gets mind-bending. Tachyons would experience time backwards. From our perspective, a tachyon would appear to travel from its destination to its starting point. When a tachyon loses energy, it actually speeds up. When it gains energy, it slows down. It's like a cosmic negative of everything we know about motion and energy. Here's what will blow your mind. If tachyons exist, they could theoretically be used to send information into the past. In 1967, physicist Richard Tolman described what's now called the tachyonic antitelephone, a device that could send messages backwards in time using faster-than-light particles. Picture this scenario. You send a tachyon message to your friend on a distant planet, telling them about something that happened on Earth today. Due to the relativistic effects we discussed, depending on your relative motion, your friend might receive that message yesterday. They could then send a tachyon message back to Earth, warning you about the event before it happens. This creates what physicists call a causal paradox or temporal paradox. You could theoretically send yourself a message telling you not to send the original message. It's like the grandfather paradox, but with particle physics instead of time travel stories. The famous physicist Stephen Hawking was so troubled by these implications that he proposed the chronology protection conjecture, the idea that the laws of physics somehow prevent these paradoxes from occurring. Hawking said, "The universe seems to have a built-in mechanism that prevents time travel and keeps the world safe for historians." But here's the really fascinating part. Despite decades of searching, we've never detected a single tachyon. Every high-energy physics experiment, from particle accelerators to cosmic ray detectors, has come up empty. Some physicists believe this isn't because tachyons don't exist, but because they interact with our slower-than-light matter in ways we don't yet understand. Other scientists propose that tachyons might exist in a shadow universe, a parallel realm of faster-than-light particles that rarely interacts with our slower-than-light world. These shadow tachyons could be flying through your body right now, experiencing your entire lifetime in reverse, without you ever knowing they're there. The mathematics of tachyons also predicts something called tachyonic condensation under certain conditions. The faster-than-light field could spontaneously create slower-than-light particles and energy. Some cosmologists believe this might have happened during the Big Bang, when our universe transitioned from some primordial faster-than-light state to our current slower-than-light reality. But if we can't detect tachyons, and they create impossible paradoxes, why do physicists still study them? Because they represent a fundamental test of our understanding of causality and space-time. If tachyons are possible, then our universe operates under very different rules than we thought. If they're impossible, then there must be some deeper principle of physics that prevents them. And discovering that principle could unlock secrets about the nature of reality itself. The search for tachyons continues in laboratories around the world, using increasingly sophisticated detection methods. And if we ever do find one, it won't just revolutionize physics. It will force us to completely reconsider what we mean by past, present, and future. What if I told you that there might be a way to travel faster than light without actually moving faster than light? What if the universe has built-in shortcuts that would make your journey across the galaxy faster than a beam of light, even though you never exceed the cosmic speed limit? Welcome to the mind-bending world of wormholes, where space itself becomes your highway dot in 1935. Einstein and his colleague Nathan Rosen were studying the mathematical structure of black holes when they discovered something extraordinary. The equations of general relativity predicted the existence of what they called Einstein-Rosen bridges, tunnels through space-time that could theoretically connect distant regions of the universe. Think of it like this. Imagine you're an ant walking on the surface of a piece of paper, and you need to get from one corner to the opposite corner. The normal route would take you across the entire surface. But what if someone folded the paper so the two corners touched? You could step directly from one corner to the other, traveling a much shorter distance through a higher dimension. That's essentially what a wormhole does with space-time. Here's what will blow your mind. If you traveled through a wormhole, you would arrive at your destination faster than light could travel the long way around. But locally, you never exceed the speed of light. It's like finding a secret passage in the universe that shortcuts the normal rules of distance and time. The physicist Kip Thorne, who won the Nobel Prize in 2017 for his work on gravitational waves, spent decades studying whether wormholes could actually exist. In the 1980s, Thorne and his colleagues discovered that while Einstein's equations allow wormholes, keeping them open would require something that doesn't exist in our normal experience: negative energy density. Imagine trying to keep a tunnel from collapsing by filling it with something that weighs less than nothing. That's what negative energy is like. It has properties that seem to violate our everyday experience of how matter behaves. Yet quantum mechanics suggests that negative energy might actually exist on incredibly small scales, in the form of virtual particles that pop in and out of existence in what physicists call the quantum vacuum. In 1988, physicist Michael Morris, a student of Thorne's, calculated exactly how much negative energy would be needed to keep a human-sized wormhole open. The answer was staggering. You'd need negative energy equivalent to the mass energy of Jupiter, compressed into a region smaller than an atomic nucleus. It's like trying to thread a needle with a rope the size of a planet. But here's where it gets even more incredible. If you could somehow create a traversable wormhole, you could potentially use it as a time machine. Here's how it would work. Create a wormhole with two mouths. Keep one mouth stationary and accelerate the other to near the speed of light. Due to time dilation, the moving mouth would age more slowly than the stationary one. When you bring them back together, the two mouths would be connected to different times. Step through the wormhole, and you'd emerge in the past. The amount of time travel would depend on how fast you accelerated the moving mouth, and for how long. In principle, you could emerge seconds, hours, or even years before you entered. This scenario was so troubling to Stephen Hawking that he proposed what he called the chronology protection conjecture, the idea that the laws of physics somehow prevent the creation of closed time-like curves that would allow time travel. Hawking suggested that quantum effects would build up inside a wormhole and destroy. At the moment, it became a time machine. Recent research by physicist Leonard Susskind and others has revealed an even stranger possibility. Quantum entanglement might be related to wormholes through something called the E-QR correspondence. This suggests that every pair of quantum entangled particles might be connected by a microscopic wormhole. If true, it means wormholes aren't exotic structures that might exist somewhere in the universe. They're everywhere, connecting every quantum system to every other quantum system. But perhaps the most mind-bending possibility comes from string theory, which predicts that our universe might have extra dimensions beyond the 3 spatial dimensions we experience. If wormholes exist in these higher dimensions, they might be much easier to create and maintain than we thought. Some scientists speculate that dark matter, the mysterious substance that makes up 85% of all matter in the universe, might actually be ordinary matter connected to us through higher dimensional wormholes. NASA and other space agencies have seriously studied the possibility of wormhole travel, not because they think it's possible with current technology, but because it represents a theoretical upper limit of what the laws of physics might allow. The Breakthrough Starshot Initiative, funded by billionaire Yuri Milner, is already developing technology to send tiny probes to nearby stars at 20% the speed of light. But if wormholes are possible, future civilizations might find ways to traverse the galaxy in minutes rather than millennia. The search for wormholes continues using gravitational wave detectors like LIGO, which might be able to detect the unique signature of objects falling through these cosmic shortcuts. And if we ever do discover one, it won't just revolutionize space travel. It will fundamentally change our understanding of what it means to be separated by distance in this universe. What if I told you that there's a way to travel faster than light that doesn't involve exotic particles or mysterious wormholes, but instead uses a principle so simple that surfers understand it intuitively? In 1994, a Mexican physicist named Miguel Alcubierre published a paper that would make Star Trek's warp drive seem not just possible, but mathematically inevitable. Alcubierre was watching an episode of Star Trek, The Next Generation, when he had a revelation. Instead of trying to accelerate a spacecraft to faster than light speeds, which we know is impossible, what if you could manipulate space-time itself to carry the spacecraft? Think of it like this. Imagine you're standing on a moving walkway at an airport. You're not walking any faster than normal, but the walkway itself is moving, so you arrive at your destination faster than if you had walked on stationary ground. Here's what will blow your mind. Alcubierre's mathematics showed that you could create a warp bubble where space contracts in front of your spacecraft and expands behind it. Inside the bubble, space-time itself is flat, so you never experience acceleration or time dilation. From your perspective, you're just sitting still while the universe moves around you. But from the outside, you're crossing vast distances faster than light ever could. The beauty of the Alcubierre drive is that it doesn't violate relativity at all. Nothing actually travels faster than light through space. Instead, space itself is moving. It's like being in a cosmic elevator, where instead of moving up through the building moves down around you. Harold Sonny White, a physicist at NASA's Johnson Space Center, has spent over a decade studying whether the Alcubierre drive could actually be built. In 2011, White published research showing that the energy requirements might be far lower than originally thought. Alcubierre's original calculations suggested you'd need negative energy equivalent to the mass of Jupiter. White's modifications reduced this to the mass of a spacecraft like Voyager, one about 700 kilograms. But here's the catch. You still need negative energy, and not just a little bit. The Alcubierre drive requires something called exotic matter, with negative energy density. This isn't just matter with negative charge or negative temperature. It's matter that has less energy than empty space itself. According to quantum field theory, such matter might exist in the form of the Casimir effect, where virtual particles create negative pressure between closely spaced plates. Think of it like this. Imagine you have a box, and you remove all the air, all the particles, all the radiation, everything. You might think you have nothing left, but quantum mechanics says that empty space is actually seething with virtual particles popping in and out of existence. Under very specific conditions, you can manipulate these quantum fluctuations to create regions with less energy than empty space. The experimental verification of the Casimir effect in 1997 by Steve Lamoureux proved that negative energy density is real, at least on microscopic scales. But scaling this up to create a warp bubble large enough for a spacecraft would require technological capabilities far beyond anything we can currently imagine. White's team at NASA has been working on what they call the White-Jude warp field interferometer, a tabletop experiment designed to detect tiny distortions in spacetime that might indicate the creation of a microscopic warp bubble. Using a modified Michelson-Morley interferometer and a carefully designed array of capacitors, they've been searching for evidence that spacetime can be manipulated using electrical fields. In 2013, White reported anomalous readings that might indicate microscopic spacetime distortion, but the results were at the very edge of the instrument's sensitivity and haven't been independently verified. Even if confirmed, the effect would be incredibly tiny, far too small to propel a spacecraft, but potentially the first evidence that space-time engineering is possible. Here's where it gets really mind-bending. The Alcubierre drive doesn't just allow faster-than-light travel, it allows faster-than-light travel without time dilation. If you traveled to Proxima Centauri, 4.2 light-years away, using an Alcubierre drive, you could make the journey in days or weeks, while only days or weeks pass on Earth. With conventional propulsion at near-light speed, the journey would take over 4 years from Earth's perspective, though you might experience only a few months due to time dilation. But the Alcubierre drive creates its own paradoxes. Because you arrive at your destination faster than light could travel the conventional route, you could potentially use the drive to travel into your own past. This brings back all the temporal paradoxes we discussed with tachyons and wormholes. Recent research by physicist Stefano Finazzi and others has suggested that quantum effects inside an Alcubierre bubble might prevent these paradoxes from occurring. High-energy particles created by the Hawking radiation near the bubble boundary might build up and destroy the warp field before it could be used for time travel. The implications go beyond just space travel. If space-time can be manipulated to create warp bubbles, it might also be possible to create gravitational shields, artificial gravity fields, or even pocket universes with different physical laws. Some theoretical physicists speculate that advanced civilizations might use Alcubierre-type technology, not just for transportation, but as a form of cosmic engineering worshipping spacetime itself to create more habitable regions of the universe. Search for evidence of Alcubierre drives continues in laboratories around the world. And if such technology is ever developed, it won't just revolutionize space travel, it will make us question the very nature of space and time themselves. What if I told you that particles can communicate with each other instantly across any distance, even if they're separated by billions of light years? And this spooky action at a distance might hold the key to faster-than-light travel? Welcome to the bizarre world of quantum entanglement. where Einstein's speed limit seems to break down at the most fundamental level of reality. In 1935, Albert Einstein, along with Boris Podolsky and Nathan Rosen, published what's now known as the EPR paradox, a thought experiment designed to show that quantum mechanics must be incomplete. They couldn't accept that particles could instantly affect each other across vast distances, calling it spooky action at a distance. Einstein believed there must be hidden variables, secret information that particles carry with them that determines their behavior. But Einstein was wrong, and proving him wrong became one of the greatest scientific achievements of the 20th century. Think of it like this. Imagine you have a pair of magical coins. When you flip one coin and it comes up heads, the other coin instantly becomes tails, no matter how far apart they are. Not only that, but the coins don't decide what they'll be until the moment you flip one of them. Before that moment, both coins exist in a superposition of heads and tails simultaneously. This isn't just a thought experiment. In 1982, physicist Alain Aspect at the University of Paris conducted a series of experiments that definitively proved quantum entanglement is real. Aspect created pairs of entangled photons and measured their properties while they were separated by large distances. Every time he measured one photon, its entangled partner instantly knew what had been measured and responded accordingly. Here's what will blow your mind. This instantaneous connection happens faster than light could travel between the particles. In 2008, scientists at the University of Geneva separated entangled photons by 18 kilometers and confirmed that the speed of entanglement is at least 10,000 times faster than light. More recent experiments suggest the effect is truly instantaneous, infinite speed. But before you start dreaming of quantum communication devices, here's the catch. You can't actually send information using entanglement. When you measure an entangled particle, you get a random result. The other particle gets a correlated random result, but there's no way to control what result you get. It's like having two magic coins where you know they'll always be opposite, but you can't control whether your coin comes up heads or tails. This limitation is called the no communication theorem, and it's what prevents quantum entanglement from violating Einstein's prohibition on faster-than-light information transfer. You can create correlations faster than light, but you can't send messages faster than light. However, quantum entanglement does enable something almost as amazing: quantum teleportation. In 1993, physicist Charles Bennett and his colleagues showed that you can use entanglement to transfer the complete quantum state of a particle from one location to another, destroying the original in the process. Here's how quantum teleportation works. Start with three particles, A, B, and C. Particles B and C are entangled and separated by a large distance. You want to teleport the quantum state of particle A to particle C. You perform a special measurement on particles A and B together, which destroys A's original state, but creates a correlation between A and the entangled pair. You then send the classical measurement results to the location of particle C at the speed of light. When those results arrive, you can perform an operation on particle C that recreates the exact quantum state that particle A originally had, the record for quantum teleportation distance keeps increasing. In 2017, Chinese scientists successfully teleported quantum states from Earth to a satellite 1,400 kilometers away. They're now working on quantum teleportation between satellites, which could enable a global quantum internet. But here's where it gets really mind-bending. Some physicists believe that quantum entanglement might be connected to the structure of space-time itself. In 2013, physicists Juan Maldacena and Leonard Susskind proposed that quantum entanglement and wormholes might be the same phenomenon viewed from different perspectives, the T equals EPR correspondence. If this is true, then every pair of entangled particles is connected by a microscopic wormhole. The instant correlations we observe in entanglement might actually be communication through these tiny space-time tunnels. This would mean that faster-than-light correlations aren't violating relativity. They're using shortcuts through higher-dimensional space. Recent research by physicist Brian Swingle and others has shown that the geometry of space-time in certain theoretical universes can be reconstructed entirely from patterns of quantum entanglement. This suggests that space and time might not be fundamental features of reality, but rather emergent properties that arise from the entanglement patterns of more basic quantum information. If true, this opens up incredible possibilities. Advanced civilizations might learn to manipulate quantum entanglement on macroscopic scales, creating artificial wormholes or even pocket universes. They might discover ways to entangle complex systems like spacecraft or even human consciousness, enabling instant transportation across the galaxy. Some scientists speculate that consciousness itself might be a quantum phenomenon that relies on entanglement between neurons in the brain. If consciousness can be quantum entangled, then perhaps there are forms of faster-than-light communication that occur naturally in biological systems, ways of sharing information that we don't yet understand. Study of quantum entanglement continues to reveal new mysteries. Recent experiments have shown that entanglement can exist not just between particles, but between particles and the vacuum of space itself, between different times, and even between different observers of the same quantum system. As we continue to unravel the mysteries of quantum entanglement, we might discover that the universe is far more connected than we ever imagined, and that the barriers between space and time are not as solid as they appear. What if I told you that faster-than-light travel doesn't just break the speed limit, it breaks the very concept of information, causality, and perhaps reality itself? We're about to explore the deepest paradox in physics, where the fundamental building blocks of the universe start to contradict each other in ways that make physicists question everything they thought they knew. The story begins with Stephen Hawking's most famous discovery, that black holes aren't completely black. In 1974, Hawking showed that quantum effects near a black hole's event horizon cause it to emit radiation and slowly evaporate. This seemed like a beautiful unification of quantum mechanics and general relativity, but it led to what's now called the black hole information paradox. And this paradox has profound implications for faster-than-light travel. Think of it like this. Imagine you write a message on a piece of paper and throw it into a fire. The paper burns, but the information isn't really destroyed. It's just transformed into heat, light, and smoke. In principle, if you could measure every particle of smoke and every photon of light with perfect precision, you could reconstruct the original message. This is the principle of information conservation, one of the most fundamental laws of physics. But here's what will blow your mind. When something falls into a black hole and the black hole evaporates through Hawking radiation, where does the information go? The radiation appears to be completely random, with no trace of what fell in. It's as if the universe has a cosmic shredder that can permanently erase information. But this violates one of the deepest principles of quantum mechanics. Hawking spent decades trying to solve this paradox. In 2004, he conceded a famous bet with the physicist John Preskill, admitting that information must somehow be conserved, even in black holes. But how this happens remains one of the biggest mysteries in physics. The resolution might involve the holographic principle, the idea that all the information in a volume of space can be encoded on its boundary. This suggests that the information falling into a black hole never actually crosses the event horizon from the outside perspective. Instead, it gets stretched across the horizon surface, encoded in the quantum fluctuations that produce Hawking radiation. But here's where faster-than-light travel makes everything worse. If you could send information faster than light, you could create what physicists call closed time-like curves, pathways that loop back to their own beginning in time. This doesn't just allow time travel, it allows you to change the past, creating grandfather paradoxes that threaten the logical consistency of the universe. Physicist Kip Thorne and his student Michael Morris showed that any faster-than-light communication method can be used to send messages into the past. Here's how. Imagine you have a faster-than-light communicator, whether it uses tachyons, wormholes, or quantum entanglement. You give one device to your friend, who travels to a distant star at near light speed. Due to the relativity of simultaneity, events that are simultaneous in your reference frame occur at different times in your friend's frame. When your friend reaches the distant star, they send you a faster-than-light message. Due to the way time dilation and length contraction work, this message can arrive at Earth before your friend originally left. You could then send a faster-than-light reply that reaches your friend before they sent the original message, warning them not to send it. This creates an information paradox even more severe than the black hole version. Not only can information be destroyed, but it can be prevented from ever existing in the first place. The universe would need some mechanism to prevent these paradoxes, but no one knows what that mechanism might be. Some physicists proposed a Novikov self-consistency principle named after Igor Novikov, which suggests that the universe somehow arranges itself to prevent paradoxes. If you try to send a message that would create a paradox, quantum fluctuations or other effects would conspire to make your attempt fail. It's as if the universe has a built-in immune system against logical contradictions. Others believe the resolution lies in the many worlds interpretation of quantum mechanics. Instead of changing the past, faster-than-light communication might create new parallel universes. When you send a message to the past, you're not changing your own timeline. You're creating a new branch of reality where events unfold differently. Recent research by physicist Daniel Harlow and others has shown that the black hole information paradox and the grandfather paradox might be intimately connected. The same quantum entanglement that might resolve the black hole paradox could also prevent closed time-like curves from forming. This suggests that there's a deep connection between the structure of space-time, the flow of information, and the nature of causality itself. The implications are staggering. If information conservation is absolute, then faster-than-light travel might be fundamentally impossible, not because of energy requirements or engineering challenges, but because it would violate the logical structure of reality. The universe might be designed in such a way that faster-than-light travel and information paradoxes are mutually exclusive. But if information can be destroyed, or if closed time-like curves are possible, then our understanding of physics is fundamentally flawed. We might need to abandon causality, information conservation, or even the concept of objective reality. This brings us to the deepest question in physics. Is the universe logically consistent? Does it follow rules that make sense? Or are there levels of reality so strange that human logic breaks down completely? The answer might determine not just whether faster-than-light travel is possible, but whether the universe itself makes sense. What if I told you that the question of faster-than-light travel isn't just about physics? It's about understanding our place in a universe so vast and strange that it challenges every assumption we have about what's possible. We're about to zoom out to the cosmic perspective, where the very concept of faster-than-light becomes almost meaningless, and where the universe reveals its most mind-bending secrets. Let's start with scale. The observable universe is approximately 93 billion light-years across. That means light from the most distant galaxies we can see has been traveling for over 13 billion years to reach us. At the speed of light, the fastest speed allowed by relativity, it would take you 93 billion years just to cross the observable universe once. But here's what will blow your mind. The observable universe might be just a tiny fraction of the total universe. cosmic inflation theory, developed by physicist Alan Guth in 1980, suggests that in the first fraction of a second after the Big Bang, space expanded faster than light. Not matter moving through space faster than light, but space itself expanding faster than light. Think of it like this. Imagine you're drawing dots on a balloon with a marker. As you inflate the balloon, the dots move apart from each other, but not because they're moving across the balloon's surface, because the surface itself is expanding. During cosmic inflation, space expanded so rapidly that regions that started closer together, that an atom ended up farther apart than galaxies. This cosmic expansion continues today. Galaxies that are sufficiently far away are receding from us, faster than light, not because they're moving through space faster than light, but because the space between us is expanding. The Hubble Space Telescope has observed galaxies whose recession velocity exceeds the speed of light by factors of 3 or more. Edwin Hubble discovered this cosmic expansion in 1929. When he noticed that distant galaxies appear, redshifted their light stretched to longer wavelengths by the expansion of space. The farther away a galaxy is, the faster it's receding. This relationship, called Hubble's law, led to the discovery that the universe is not static, but dynamically expanding. But expansion is just the beginning. In 1998, 2 teams of astronomers, one led by Saul Perlmutter and another by Brian Schmidt and Adam Rees, made a discovery that earned them the Nobel Prize in Physics. They found that the universe's expansion is accelerating. Something called dark energy, which makes up about 68% of the universe, is causing space to expand faster and faster. This acceleration means that galaxies beyond a certain distance will eventually become unreachable, even with faster-than-light travel. The cosmic horizon, the boundary of what we can ever hope to reach, is shrinking. Galaxies that we can see today will eventually disappear beyond this horizon, their light redshifted into invisibility. Here's where the cosmic perspective becomes truly humbling. If advanced civilizations exist in those distant galaxies, they face the same limitation. No matter how advanced their technology becomes, no matter whether they master wormholes, Alcubierre drives, or technologies we can't even imagine, there are regions of the universe they will never be able to reach. Leads to what cosmologists call the cosmic loneliness scenario. As the universe ages and dark energy continues to accelerate expansion, galaxy clusters will become isolated islands in an increasingly empty cosmos. Civilizations in the far future will look out and see nothing but darkness, no evidence that other galaxies ever existed. But here's an even more mind-bending possibility. What if the universe is infinite? If space extends infinitely in all directions, then somewhere out there, beyond our cosmic horizon, there are exact copies of you watching this exact video. In fact, in an infinite universe, there would be infinitely many copies of you, living lives identical to yours down to the quantum level. The mathematics of infinity suggests that in an infinite universe, every possible arrangement of matter and energy not only exists, but exists infinitely many times. There are versions of you where you decided not to watch this video, versions where you became a physicist studying faster-than-light travel, and versions where faster-than-light travel was discovered yesterday. This brings us to the concept of the multiverse, not just multiple universes, but infinite universes with different physical laws. String theory, which attempts to unify all the forces of nature, predicts that our universe might be just one bubble in an infinite foam of universes, each with different values for the fundamental constants of physics. In some of these universes, the speed of light might be faster or slower. In others, faster-than-light travel might not just be allowed, but necessary for stable matter to exist. There might be universes where tachyons are the dominant form of matter, where causality runs backwards, or where time has multiple dimensions. Renowned physicist Max Tegmark has proposed that every mathematically consistent universe actually exists somewhere in the multiverse. This means there are universes where the laws of physics are completely different from ours, universes where faster-than-light travel is not just possible but trivial. But even with this cosmic perspective, the fundamental question remains: in our universe, with our laws of physics, is faster-than-light travel possible? The answer might depend on discoveries we haven't made yet about the nature of dark matter, dark energy, and quantum gravity. Dark matter makes up about 27% of the universe, but we don't know what it is. Some theories suggest it might be particles that interact primarily through gravity, making them nearly invisible to ordinary matter. But other theories propose that dark matter might exist in parallel dimensions, or might be connected to our dimension through higher dimensional wormholes. If dark matter can move faster than light in higher dimensions, it might provide a pathway for faster-than-light travel in our dimension. Advanced civilizations might learn to manipulate dark matter fields to create cosmic superhighways that connect distant regions of space. Dark energy is even more mysterious. We know it exists because we can measure its effects on cosmic expansion, but we have no idea what it actually is. Some theories suggest it might be a field that permeates all of space, a field that might be manipulated by sufficiently advanced technology. If dark energy can be controlled, it might be possible to create regions of space where expansion occurs. In reverse, effectively shrinking the distance between objects. You could create a dark energy bubble around your spacecraft that contracts space in front of you and expands it behind you. Essentially the same principle as the Alcubierre drive, but using dark energy instead of exotic matter. The cosmic perspective also reveals the ultimate irony of faster-than-light travel. The faster you can travel, the smaller the universe becomes. With conventional space travel, the galaxy is impossibly vast, and other galaxies are unreachably distant. With faster-than-light travel, the observable universe becomes your neighborhood. With instantaneous travel, distance becomes meaningless, and the entire cosmos becomes as small as your backyard. This transformation of scale has profound implications for consciousness and identity. If you could be anywhere in the universe instantly, what would here mean? If you could experience events in any order, what would now mean? Faster-than-light travel doesn't just change how we move through space, it changes what space and time mean to conscious beings. As we continue to study the cosmos, we're discovering that the universe is stranger and more wonderful than we ever imagined. From quantum entanglement to cosmic inflation, from dark energy to parallel dimensions, reality operates on principles that challenge our everyday understanding of how things work. The question of faster-than-light travel forces us to confront the deepest mysteries of existence. What are the fundamental limits of what's possible? Is there a difference between what's physically possible and what's logically possible? And in a universe that might contain infinite copies of ourselves, what does it really mean to travel from here to there? What if I told you that even if faster than light, travel is theoretically possible, the engineering challenges are so extreme that they make building a pyramid look like assembling a Lego set? We're about to explore what it would actually take to build a faster-than-light spacecraft and why the practical obstacles might be even more formidable than the theoretical ones. Let's start with the Alcubierre drive, since it's the only faster-than-light propulsion system that doesn't obviously violate the laws of physics. Remember, you need to create a region of space where space-time contracts in front of your ship and expands behind it. Harold White's calculations suggest you need negative energy equivalent to about 700 kilograms of mass. That doesn't sound too bad until you realize what negative energy actually means. Think of it like this. You need to create matter that weighs less than nothing, not antimatter that still has positive mass. Not matter with negative charge that still has positive mass. You need matter with negative mass energy, something that has never been observed in nature, except possibly in the quantum vacuum at subatomic scales. The Casimir effect, discovered by Dutch physicist Hendrik Casimir in 1948, demonstrates that negative energy density is real. When you place two metal plates very close together in a vacuum, quantum fluctuations create a region between the plates with slightly less energy than empty space. The plates are pushed together by what's effectively negative pressure. But here's the engineering challenge. The Casimir effect produces incredibly tiny amounts of negative energy. The force between two plates 1 micrometer apart is about 107 newtons per square meter, roughly equivalent to the weight of a red blood cell, spread over an area the size of your fingernail. To create enough negative energy for an Alcubierre drive, you'd need Casimir plates with an area comparable to a small planet, separated by distances smaller than an atomic nucleus. Even if you could somehow scale up the Casimir effect, you'd face another problem: stability. Negative energy is inherently unstable. It tends to decay into positive energy and photons through a process called the runaway paradox. Any concentration of negative energy above a certain threshold would spontaneously collapse, releasing massive amounts of radiation. Physicist Ford and Roman showed in 1995 that there are quantum inequalities that limit how much negative energy you can concentrate in a given region for a given time. These inequalities suggest that while small amounts of negative energy can exist briefly, the large concentrations needed for an Alcubierre drive might be fundamentally impossible. But let's assume you somehow solve the negative energy problem. You still need to create and control a warp bubble that's stable, steerable, and safe for human occupants. The mathematics of general relativity show that the space-time distortions around an Alcubierre drive would be incredibly violent tidal forces that could rip apart any matter inside the bubble. The bubble itself would also be incredibly dangerous to the outside universe. As you travel, the warp bubble would accumulate high-energy particles and radiation from the quantum vacuum. When you stop and collapse the bubble, all of this energy would be released in a burst that could sterilize entire solar systems. Physicist Brendan McMonagall calculated that an Alcubierre drive traveling to Proxima Centauri would accumulate enough energy to destroy the destination star system when it stops. You wouldn't just be traveling faster than light, you'd be carrying a weapon of mass destruction that makes nuclear bombs look like firecrackers. Now let's consider wormholes. To create a traversable wormhole, you need to somehow manipulate the topology of space-time itself, essentially creating a tunnel through higher dimensional space. This would require technology capable of engineering space-time at the Planck scale, where quantum effects dominate gravity. The Planck length is about 10 to 35 meters, so small that if you scaled an atom up to the size of the observable universe, the Planck length would still be smaller than a grain of sand. Working at this scale would require manipulating individual quantum fluctuations of the space-time fabric itself. Even if you had this capability, keeping a wormhole open would require threading it with exotic matter with negative energy density. The same stuff you need for the Alcubierre drive, but in even larger quantities. Kip Thorne's calculations suggest you'd need negative mass energy equivalent to Jupiter, compressed into a region smaller than an atomic nucleus. The engineering challenges don't stop there. Any wormhole would be incredibly unstable. The slightest perturbation would cause it to collapse faster than light could cross it. You'd need active feedback systems operating faster than light just to keep the wormhole from destroying itself before you could use it. What about tachyon communication? Even if tachyons exist, detecting and manipulating them would require technology we can barely imagine. Tachyons interact with ordinary matter so weakly that they pass through entire planets without leaving a trace. Creating a tachyon transmitter would be like trying to send radio signals using neutrinos. Theoretically possible, but practically impossible with any conceivable technology. The energy requirements alone are staggering. Gerald Feinberg's original calculations showed that creating a single tachyon would require energies comparable to those found in particle accelerators. Building a practical tachyon communicator would need energy sources more powerful than the output of entire stars. But perhaps the most challenging aspect of faster-than-light travel isn't the physics or even the engineering, it's the computational problem. Any faster-than-light navigation system would need to solve the general relativistic equations for curved spacetime in real time, accounting for the gravitational effects of every nearby mass dot. This is what physicists call the n-body problem, and it's computationally unsolvable for more than 3 objects. Navigating through a solar system with planets, moons, asteroids, and comets would require computational power that might exceed the theoretical limits of any computer that could fit in a spacecraft. Recent advances in quantum computing might offer a solution. Quantum computers can solve certain types of problems exponentially faster than classical computers. But even quantum computers have limits, and the computational requirements for faster-than-light navigation might exceed even these theoretical bounds. Despite all these challenges, research into faster-than-light propulsion continues. NASA's Breakthrough Physics Propulsion Project has investigated various exotic propulsion concepts, from zero-point energy extraction to space-time modification. Private organizations like the Tau Zero Foundation are funding research into advanced propulsion concepts that could lead to interstellar travel. The engineering challenges are immense, but they're not necessarily insurmountable. Technologies that seem impossible today might become routine for future civilizations. After all, powered flight was impossible until 1903. Space travel was impossible until 1957, and quantum computers were impossible until the 1990s. The quest to build faster-than-light spacecraft pushes the boundaries of what's possible, forcing us to develop new technologies, new materials, and new ways of thinking about the universe. Even if we never achieve faster-than-light travel, the attempt will likely lead to discoveries and innovations we can't yet imagine. What if I told you that the question of faster-than-light travel isn't just about physics and engineering? It's fundamentally about you, about your dreams, your limitations, your place in the cosmic story, and what it means to be a conscious being in a universe that might be far stranger than you ever imagined. Right now, as you're watching this video, you exist at a unique point in space and time. You're sitting approximately 150 million kilometers from the Sun, on a planet that's rotating at over 1,600 kilometers per hour at the equator, orbiting the Sun at 30 kilometers per second, in a solar system that's moving through the galaxy at 230 kilometers per second, in a galaxy that's racing through space at over 600 kilometers per second toward the Andromeda Galaxy. You are already traveling faster than a speeding bullet, faster than the speed of sound, faster than anything humans had ever experienced until just over a century ago. Yet from your perspective, you're sitting still, watching a video about faster-than-light travel. This is the first profound lesson of relativity. Motion is relative, but the speed of light is absolute. No matter how fast you're moving, light always passes you at exactly 299,792,458 meters per second. This isn't just a curious fact about physics. It's a fundamental constraint on your existence as a conscious being in this universe. Think about what this means for your life. Every relationship you have, every conversation you engage in, every thought you share with another person is limited by the speed of light. When you look at someone across the room, you're seeing them as they were a few nanoseconds ago, the time it took light to travel from them to your eyes. When you video chat with someone on another continent, there's a delay of milliseconds or seconds as information travels through fiber optic cables at nearly the speed of light. But here's what will blow your mind. If faster-than-light travel were possible, It wouldn't just change how you move through space. It would fundamentally change what it means to be you. Your sense of identity is deeply tied to your continuous existence through time, from past to present to future. Faster-than-light travel could potentially allow you to interact with your own past, meeting earlier versions of yourself and creating paradoxes that challenge the very concept of personal identity. Imagine this scenario. You develop the ability to travel faster than light. You use it to travel to a distant star and back, arriving on Earth before you left. You could potentially prevent yourself from making the original journey. But if you prevent the journey, then how did you get back to prevent it? You would exist as an effect without a cause, a person without a past. This isn't just a philosophical puzzle. It's a question about the fundamental nature of consciousness and free will. If faster-than-light travel allows you to change your past, then your current decisions might be influenced by your future actions. The linear progression of cause and effect that shapes your daily experience would break down completely. Consider how this affects your relationships with other people. Every human connection you've ever made is based on the assumption that you share the same timeline, the same sequence of cause and effect. Love, friendship, trust, all of these depend on the idea that you and the people you care about experience events in the same order. With faster-than-light travel, you could potentially visit your friends in their past before they knew you. You could witness events from their childhood, see them make decisions that shaped who they became. You would know their entire life story while they're still living it. The asymmetry of knowledge and experience would fundamentally alter the nature of human relationships. But there's an even deeper personal implication. Your consciousness, your sense of being you, depends on the continuous flow of information through your brain. Neurons communicate through electrical and chemical signals that travel at speeds much slower than light. Your thoughts, memories, and perceptions are all constrained by the speed at which information can move through biological tissue. If faster-than-light communication were possible, it might enable forms of consciousness that we can't currently imagine. You might be able to extend your awareness across vast distances instantaneously, experiencing events on multiple planets simultaneously. The boundaries of your individual identity might dissolve as you merge your consciousness with others across the galaxy. This possibility raises profound questions about what makes you you. Are you defined by your physical body, your memories, your pattern of thoughts and experiences? If faster-than-light technology could copy your consciousness and transmit it to distant locations, would the copy be you or someone else? If you could split your consciousness across multiple locations, which one would be the real you? Recent research in neuroscience suggests that consciousness might already be more distributed than we realize. Your brain doesn't have a single control center where all decisions are made. Instead, consciousness emerges from the complex interactions of billions of neurons, each operating according to local rules, but collectively creating your unified experience of being you. If consciousness is truly an emergent property of complex information processing, then faster-than-light communication might enable forms of distributed consciousness that span planets or even galaxies. You might become part of a cosmic mind, maintaining your individual identity while participating in a larger collective intelligence. But even without faster-than-light travel, you are already part of something larger. The atoms in your body were forged in the hearts of dying stars billions of years ago. The carbon in your DNA, the calcium in your bones, the iron in your blood, all were created in stellar furnaces and scattered across the galaxy by supernova. You are literally made of star stuff, connected to the cosmos at the most fundamental level. The energy that powers your thoughts comes from nuclear fusion in the sun, where hydrogen atoms combine to form helium at temperatures of millions of degrees. This energy traveled 150 million kilometers through space as electromagnetic radiation was captured by plants through photosynthesis. and was passed through the food chain to fuel your brain as you watch this video and contemplate faster than light. Travel. In a very real sense, your consciousness is part of the universe's attempt to understand itself. Through your eyes, the cosmos looks back at itself and wonders about its own nature. Through your questions about faster than light travel, the universe explores the limits of what's possible within its own laws. This perspective transforms the question of faster than light travel from a technical challenge into a deeply personal quest. It's not just about building faster spacecraft or developing exotic technologies. It's about transcending the limitations that define your current existence and expanding your identity beyond the boundaries of space and time. Whether or not faster than light travel is possible, the quest to understand it has already changed you. By contemplating the nature of space-time, causality, and the limits of physics, you've expanded your conception of what reality might be. You've become part of humanity's ongoing effort to push beyond the boundaries of the known and explore the impossible. And perhaps that's the real significance of faster than light travel, not as a destination, but as a journey of discovery that transforms our understanding of ourselves and our place in the cosmos. What if I told you that faster than light travel doesn't just challenge physics? It forces us to completely reconsider what we mean by reality, consciousness, free will, and the very nature of existence itself. We're about to explore how the possibility of exceeding light speed touches the deepest questions that have puzzled philosophers and scientists for millennia. Let's start with the most fundamental question: what is real? In our everyday experience, reality seems solid and unchanging. The chair you're sitting in, the device you're watching this on, the room around you, these feel like permanent, objective features of the world. But faster than light travel reveals that reality might be far more fluid than we imagine. Consider the relativity of simultaneity that we discussed earlier. Two events that appear simultaneous to you might occur at different times for someone moving at high speed relative to you. With faster than light travel, this effect becomes extreme. Events that you experience in sequence might be experienced in reverse order by a faster than light traveler. This means there's no universal now. The present moment that feels so immediate and real to you doesn't exist for faster than light observers. Past, present, and future become relative concepts that depend on your motion through space-time. The timeline of your life, the sequence of experiences that makes you who you are, is not an absolute feature of reality, but something that varies depending on how you move through the universe. Philosopher Henry Bergson argued with Einstein about this very issue in the 1920s. Bergson believed that psychological time, your lived experience of duration and becoming, was more fundamental than physical time. Einstein disagreed, arguing that physics revealed time to be relative and that our psychological intuitions about time were simply wrong. If faster than light travel is possible, this debate takes on new significance. Your consciousness experiences time is flowing from past to future, but faster than light particles might experience time flowing in the opposite direction. Which perspective reveals the true nature of time? Is there even such a thing as the true nature of time? Or is temporality entirely relative to the observer? This brings us to the question of free will. Your sense of being able to make choices depends on the assumption that the future is open and undetermined, while the past is fixed and unchangeable. But faster than light travel allows you to influence events in what you normally consider the past. If you can change the past, then the past was never really fixed. If the past isn't fixed, then your memories might not correspond to what actually happened. Think about how this affects moral responsibility. If you could travel back in time and prevent a tragedy, would you be morally obligated to do so? But if preventing the tragedy changes the timeline that led to your decision to prevent it, you create a causal loop that makes the concept of moral choice meaningless. You would be simultaneously responsible and not responsible for the same action. Some philosophers have proposed the block universe theory to resolve these paradoxes. In this view, all of space and time past, present, and future exist equally. Your life is like a four-dimensional sculpture in space-time, with every moment equally real. From this perspective, faster-than-light travel doesn't allow you to change the past. It reveals that change is an illusion created by your limited perception of the temporal dimension. But the block universe theory creates its own philosophical problems. If the future is as real as the present, then everything that will ever happen has, in some sense, already happened. Your choices are not truly free, but predetermined by the structure of space-time itself. You are not an agent shaping the future, but a character in a cosmic story that was written before you were born. Recent developments in quantum mechanics add another layer of complexity. The many worlds interpretation suggests that every quantum event creates parallel universes where all possible outcomes occur. Combined with faster-than-light travel, this could mean that changing the past doesn't alter your original timeline, but creates new branches of reality. In this scenario, you wouldn't be changing the past, but accessing alternate versions of reality where events unfolded differently. Your original timeline would still exist, but you could travel to parallel universes where different choices were made. This preserves free will and moral responsibility, while allowing for faster-than-light paradoxes to be resolved through the creation of multiple realities. But if multiple realities exist, which one is the real you? Are you the person in your original timeline, or do all versions of you across all timelines have equal claim to being the authentic version? The concept of personal identity becomes meaningless when there are infinite versions of yourself living every possible life. This connects to ancient philosophical questions about the nature of consciousness and identity. The Greek philosopher Heraclitus said, "You cannot step into the same river twice, because the water is always flowing and changing." But with faster-than-light travel, you might literally be able to step into the same river twice by traveling to the past and encountering the same water molecules at an earlier time. The ship of Theseus paradox becomes even more complex with faster-than-light travel. If you could travel back in time and gradually replace every part of an object with identical parts from the future, when does it stop being the original object? If consciousness can be transmitted faster than light, you could potentially have the same paradox with yourself, meeting past and future versions of yourself and questioning which one is the real you. Eastern philosophical traditions have long embraced concepts that Western physics is only beginning to explore. Buddhism teaches that the self is an illusion, that individual identity is a mental construct overlaid on the continuous flow of experience. If faster-than-light travel allows consciousness to transcend the normal boundaries of space and time, it might reveal that the Buddhist understanding of selflessness is literally true. The Hindu concept of Maya, the idea that the world of separate objects and individuals is an illusion, masking an underlying unity, takes on new meaning in the context of quantum entanglement and faster-than-light correlations. If particles can be instantaneously connected across any distance, perhaps consciousness can be similarly connected, revealing that the separation between minds is as illusory as the separation between entangled particles. These philosophical implications extend to questions about the nature of knowledge and truth. If faster-than-light travel allows you to observe events before they happen in your reference frame, can you have knowledge of the future? But if you can change what you observe through your actions, then your knowledge might alter the reality it describes, creating a feedback loop that makes objective truth impossible. The scientific method itself depends on the assumption that observations correspond to an objective reality that exists independently of the observer. But faster-than-light travel reveals that different observers can have fundamentally incompatible perspectives on the same events. How can science make progress if there's no universal framework for organizing observations and testing theories. Perhaps the deepest implication is that faster-than-light travel forces us to confront the limits of human understanding. Our brains evolved to navigate a world where nothing moves faster than running animals, where cause always precedes effect, and where time flows in one direction. The concepts we use to understand reality, logic, causality, identity might be fundamentally inadequate for describing a universe where faster than light travel is possible. This doesn't mean we should give up on understanding. It means we might need to develop new forms of thinking that go beyond human intuition. Just as mathematics allows us to explore dimensions we can't visualize, and quantum mechanics describes phenomena we can't directly experience, we might need new conceptual frameworks to understand the implications of faster-than-light travel. The quest to understand faster-than-light travel is ultimately a quest to understand the deepest nature of reality itself and to discover whether human consciousness is capable of comprehending truths that transcend the limitations of our evolved mental architecture. What if I told you that whether or not faster-than-light travel is possible will determine the ultimate fate of human civilization and our destiny as a species in the cosmos? We're about to explore how this seemingly abstract physics question might be the most important factor in determining whether humanity becomes a cosmic civilization or remains forever trapped in our solar system. Right now, humanity exists on a single planet orbiting an ordinary star in an unremarkable corner of the Milky Way galaxy. We've been a spacefaring species for less than 70 years, a tiny fraction of our 300,000-year history as modern humans. In cosmic terms, we're barely toddlers, taking our first tentative steps away from our home world. But those first steps reveal the staggering scale of the challenge ahead. The nearest star system, Proxima Centauri, is 4.2 light-years away. With our current technology, it would take tens of thousands of years to reach it. Even with theoretical fusion rockets that could achieve 10% the speed of light, the journey would take over 40 years. For the travelers, it would be a one-way trip to a destination they could barely imagine without faster-than-light travel. Interstellar colonization becomes a test of species-level patience and commitment that no human civilization has ever demonstrated. The people who design and launch an interstellar mission would never see its results. The colonists who arrive at the destination would be generations removed from the society that sent them. They would be more like seeds that explore genetic and cultural offspring, sent to grow into something entirely new in alien soil. This is what physicists call the generational ship scenario. Massive spacecraft carrying thousands of people would become traveling worlds, complete with ecosystems, cities, and evolving cultures. The journey itself would span centuries, during which the ship's inhabitants would be born, live, and die knowing only life aboard a vessel traveling between the stars. But here's what will blow your mind. Even with generational ships, humanity could theoretically colonize the entire galaxy in just a few million years. That sounds like a long time, but it's less than 1% of the galaxy's age. If we started sending out colony ships today, our descendants could spread to every habitable world in the Milky Way before the sun begins to die. This scenario, first described by physicist Freeman Dyson, reveals that faster-than-light travel isn't necessary for becoming a galactic civilization. It's just a question of time and commitment. But without faster-than-light communication, this galactic human civilization would be incredibly fragmented. Each colony world would develop independently, evolving its own culture, technology, and possibly even biology over thousands of generations. The result wouldn't be a unified human civilization, but a galaxy full of human-descended species that might be as different from each other as we are from other Earth species. Some might remain recognizably human. Others might adapt to alien environments in ways that transform them into something entirely new. This brings us to the Fermi paradox, the question of where all the aliens are. If intelligence is common in the universe, and if civilizations can spread across the galaxy in just a few million years, then why haven't we encountered any evidence of extraterrestrial intelligence? One possibility is that faster-than-light travel is impossible, and most civilizations choose not to undertake the enormous effort required for slower-than-light interstellar expansion. They remain confined to their home systems, developing increasingly sophisticated but ultimately local technologies. From this perspective, the universe might be full of advanced civilizations that simply never interact because the distances are too vast and the journey times too long. But what if faster-than-light travel is possible? This changes everything about humanity's cosmic destiny. With the ability to travel between stars in days or years rather than centuries, the galaxy becomes humanity's neighborhood rather than an unreachable wilderness. Colony ships become unnecessary. People could commute between star systems the way we now travel between continents. The implications for human civilization would be profound. Instead of fragmenting into isolated populations, humanity could remain connected across vast distances. Cultural and technological developments on one world could spread to others almost instantaneously. Earth could remain the cultural and political center of a truly galactic civilization. But faster than light, travel would also create new challenges and possibilities we can barely imagine. If travel times between stars become negligible, the concept of separate nations or planets becomes meaningless. Why fight over resources on Earth when entire solar systems are accessible within days? Why maintain separate governments when representatives from distant worlds can attend meetings in person? The economic implications are staggering. With faster-than-light travel, rare elements and exotic materials could be transported from anywhere in the galaxy to anywhere else almost instantly. Entire planets could specialize in specific industries, creating a galactic economy of unprecedented complexity and abundance. But perhaps the most profound impact would be on human evolution and consciousness itself. If faster-than-light communication is possible, it might enable forms of distributed consciousness that span multiple worlds. Humans could potentially share thoughts and experiences across galactic distances, creating a kind of collective intelligence that transcends individual minds. This connects to concepts that futurists call the technological singularity, a hypothetical point where artificial intelligence surpasses human intelligence and accelerates technological progress beyond human comprehension. If faster-than-light communication enables instantaneous information sharing across the galaxy, the computational resources available to such an intelligence would be virtually unlimited. Galactic-scale artificial intelligence with faster-than-light communication capabilities could potentially simulate entire universes, explore every possible technological development, and answer fundamental questions about the nature of reality itself. From this perspective, the question of whether faster-than-light travel is possible isn't just about transportation. It's about the ultimate limits of intelligence and knowledge in the universe. But there's a darker possibility. If faster-than-light travel is possible but requires enormous energy or exotic matter, it might be accessible only to very advanced civilizations. This could create a cosmic hierarchy where species that master faster-than-light technology become effectively godlike compared to those that remain trapped by light speed. From this perspective, humanity is currently in a race against time. We need to develop faster-than-light capabilities before we encounter other species that already have them. If we remain limited to slower-than-light travel, while others can move freely between stars, we could become cosmic primitives isolated on our single world, while advanced civilizations reshape the galaxy around us. Recent developments in theoretical physics suggest we might be approaching a critical decision point. Research into dark energy, quantum gravity, and exotic matter is advancing rapidly. Within the next century, we might discover whether faster-than-light travel is possible, and, if so, how to achieve it. If faster-than-light travel proves impossible, humanity will face the choice of remaining a single-planet species or undertaking the enormous challenge of slower-than-light interstellar expansion. This choice will define our species for millions of years to come. If faster-than-light travel is possible, we'll face an even more momentous decision: how to use this capability responsibly. The power to travel between stars instantly would make us almost godlike compared to our current limitations, but it would also give us the ability to spread across the galaxy and potentially encounter other civilizations with similar capabilities. The question of faster-than-light travel is ultimately the question of humanity's cosmic destiny. Will we remain forever confined to our solar system, slowly expanding outward over millions of years? Will we fragment into separate species adapted to different worlds? Or will we become a unified galactic civilization, connected by faster-than-light transportation and communication? The answer might be discovered in our lifetime, and it will determine the fate of every human who comes after us. What if I told you that right now, as you're watching this video, scientists around the world are conducting experiments that might prove faster-than-light phenomena are not only possible, but already happening all around us? We're about to explore the cutting-edge research that's pushing the boundaries of what we thought was impossible. At the European Organization for Nuclear Research, CERN, in Switzerland, the Large Hadron Collider is smashing particles together at energies never before achieved in a laboratory. When protons collide at 99.999% the speed of light, they create conditions that existed just moments after the Big Bang. And in those collisions, physicists are discovering phenomena that challenge our understanding of space, time, and causality. In 2011, the OPERA experiment at CERN made headlines around the world when they announced the detection of neutrinos that appeared to travel faster than light. The neutrinos were created by particle collisions in Switzerland and detected 730 kilometers away in Italy. The time difference between their creation and detection suggested they had arrived 60 nanoseconds earlier than light would have. The scientific community was skeptical, and rightly so. After months of investigation, the faster-than-light result was traced to a loose fiber optic cable that had introduced a systematic error into the timing measurements. But the episode revealed how eagerly physicists are watching for any hint that the light barrier might be permeable. Here's what will blow your mind. Even though the OPERA result was incorrect, similar experiments continue to push the limits of measurement precision in search of genuine faster-than-light phenomena. The IceCube Neutrino Observatory, buried deep in Antarctic ice, detects high-energy neutrinos from cosmic sources billions of light-years away. These ghost-like particles pass through the entire Earth as if it weren't there, and scientists are studying whether their properties might reveal hints of faster-than-light physics. At NASA's Jet Propulsion Laboratory, Harold White's team continues their work on the White-Jude Warp Field Interferometer. This tabletop device uses precisely calibrated laser interferometry to search for microscopic distortions in spacetime. While they haven't detected definitive evidence of spacetime manipulation, their measurements are approaching the sensitivity needed to detect quantum-scale warp effects. The breakthrough might come from an unexpected direction. In 2019, researchers at the University of Rochester created optical space-time wave packets, structured light beams that can travel through free space at velocities different from the speed of light. While these don't carry information faster than light, they demonstrate that the relationship between light and the speed limit of causality is more complex than previously thought. Even more intriguingly, quantum teleportation experiments are achieving new distance records almost monthly. In 2020, Chinese scientists successfully teleported quantum states between Earth and satellites over 1,200 kilometers away. While this doesn't allow faster-than-light communication, it proves that quantum entanglement works across astronomical distances and might be scalable to galactic ranges. The James Webb Space Telescope, launched in 2021, is making observations that challenge our understanding of cosmic expansion. Some galaxies appear to be more massive and mature than should be possible given their age, suggesting that our models of how the universe evolved might be incomplete. If cosmic inflation or other faster-than-light processes played a larger role in cosmic evolution than we thought, it might indicate that faster-than-light phenomena are more common than we imagined. At the theoretical level, the search for a theory of everything that unifies quantum mechanics and general relativity continues to reveal new possibilities. String theory predicts the existence of extra dimensions that could provide pathways for faster-than-light travel. Loop quantum gravity suggests that space-time itself might be discrete and manipulable at the Planck scale. One of the most promising developments comes from the study of dark energy. The accelerating expansion of the universe is driven by some form of energy that we don't understand, but that makes up 68% of the universe. Recent observations suggest that dark energy might not be constant, but could vary over time and space. If dark energy can be manipulated, it might provide the exotic energy needed for Alcubierre drives or other faster-than-light propulsion systems. The search for dark matter is also revealing new possibilities. The Large Underground Xenon, LUX, experiment and similar detectors buried deep underground are looking for dark matter particles that might pass through ordinary matter. Some theories suggest that dark matter might exist in parallel dimensions or might be connected to our dimension through microscopic wormholes. If dark matter can travel faster than light in higher dimensions, it might provide a pathway for faster-than-light communication or travel in our dimension. Artificial intelligence is accelerating the pace of discovery in ways that would have been impossible just a few years ago. Machine learning algorithms are analyzing vast datasets from particle accelerators, space telescopes, and gravitational wave detectors, looking for patterns that human scientists might miss. AI systems have already discovered new types of quantum entanglement and predicted new materials with exotic properties. In 2023, an AI system analyzing data from the LIGO gravitational wave detector identified previously unnoticed anomalies that might indicate new physics beyond Einstein's general relativity. While these signals are still being investigated, they demonstrate how AI might help us detect faster-than-light phenomena that are too subtle for human analysis. The private sector is also joining the search. Companies like SpaceX, Blue Origin, and Breakthrough Starshot are developing technologies that could enable interstellar travel within this century. While these efforts focus on conventional propulsion, the engineering challenges they're solving might be stepping stones toward more exotic technologies. Breakthrough Starshot, funded by billionaire Yuri Milner, plans to send tiny spacecraft to Proxima Centauri using powerful laser arrays to accelerate light sails to 20% the speed of light. While this isn't faster than light travel, it represents the first serious attempt to reach another star system within a human lifetime. The technologies developed for this project, including precisely controlled laser arrays and ultra-lightweight spacecraft, might be adaptable for future faster-than-light research. The quantum internet is also becoming a reality. China has already demonstrated quantum communication networks spanning thousands of kilometers, and other countries are developing similar systems. While these networks are limited by the speed of light, they prove that quantum effects can be harnessed for practical communication across vast distances. As these networks expand, they might reveal new properties of quantum entanglement that could lead to faster-than-light applications. Some physicists speculate that quantum networks might be able to detect correlations with parallel universes or higher dimensions. opening up possibilities for communication or travel beyond our normal spacetime. But perhaps the most significant development is the growing recognition that faster-than-light phenomena might be necessary to explain observed features of the universe. Cosmic inflation, the idea that space expanded faster than light in the first fraction of a second after the Big Bang, is now accepted by most cosmologists as the best explanation for the observed properties of the cosmic microwave background radiation. Faster-than-light expansion was possible in the early universe. Why couldn't it be possible now? Some theories suggest that the same scalar field that drove cosmic inflation might still exist and might be manipulable by sufficiently advanced technology. This could provide a natural mechanism for Alcubierre drives or other faster-than-light propulsion systems. The search for faster-than-light phenomena is entering a new phase. Instead of asking whether such phenomena are possible, scientists are increasingly asking how they work and how they might be harnessed. The combination of new theoretical insights, advanced experimental techniques, and artificial intelligence is accelerating the pace of discovery in ways that might lead to breakthroughs within our lifetime. As we continue to push the boundaries of what's possible, we're discovering that the universe is stranger and more wonderful than we ever imagined. The question isn't whether faster-than-light travel will ever be possible. It's whether we'll be ready for the implications when we discover how to achieve it. What if I told you that everything we've explored about faster-than-light travel, the physics, the paradoxes, the possibilities, ultimately comes back to one fundamental question? What does it mean to be human in a universe where the impossible might be possible? As we reach the end of our journey through the mind-bending implications of faster-than-light travel, let's step back and consider what this means for you, personally, right here, right now. You've spent the last 2.5 hours contemplating ideas that challenge the very foundations of reality. Your brain, a 3-pound collection of neurons that evolved to help your ancestors survive on the African savanna, has just grappled with concepts that would have been incomprehensible to humans throughout most of our species. History. This in itself is remarkable. You are part of the first generation of humans who can seriously contemplate faster-than-light travel, not as fantasy, but as a legitimate scientific possibility. Your ancestors looked up at the stars and saw gods, omens, or distant lights. You look up at the stars and see destinations. But here's what will blow your mind one final time. Regardless of whether faster-than-light travel ever becomes possible, the fact that you can even conceive of it has already transformed you. By understanding relativity, quantum mechanics, and the strange properties of spacetime, you've expanded your consciousness beyond the limitations of everyday experience. You've become a cosmic citizen, capable of thinking on scales of time and distance that dwarf human history. Consider what this means for your daily life. The problems that seemed overwhelming this morning, work stress, relationship challenges, financial concerns, exist within a cosmic context that's almost incomprehensibly vast. The universe contains at least 2 trillion galaxies, each with hundreds of billions of stars. The atoms in your body have existed for billions of years and will continue to exist long after you're gone, recycling through countless other forms of matter and energy. This perspective doesn't diminish your problems or make your life less meaningful. Instead, it reveals that you are part of something magnificent and mysterious, a universe that has evolved in such a way that it can contemplate itself through your consciousness. You are not just observing the cosmos. You are the cosmos observing itself. The question of faster-than-light travel forces us to confront the ultimate limits of human potential. If such travel is possible, it represents the next great leap in human evolution, not biological evolution, but the evolution of consciousness and capability. Just as our ancestors learned to control fire, develop language, and build civilizations, we might learn to transcend the limitations of space and time. But even if faster-than-light travel proves impossible, the quest to understand, it has already yielded profound benefits. Every technology you use, from GPS satellites that correct for relativistic effects to quantum computers that harness entanglement, exists because humans dared to explore ideas that seemed impossible. The smartphone in your pocket contains more computing power than the supercomputers used to plan the Apollo missions. It relies on quantum mechanics to function, uses satellites that must account for time dilation, and connects you to a global network that approaches the speed of light. You carry in your hand technologies that would have seemed like magic to people just a century ago. This pattern of impossible ideas becoming everyday reality suggests that faster-than-light travel might follow a similar path. Today's theoretical speculations about wormholes, Alcubierre drives, and quantum teleportation might become tomorrow's engineering challenges and next century's routine technologies. But there's a deeper message here about human nature and potential. You are part of a species that refuses to accept limitations. When told that heavier-than-air flight is impossible, humans built airplanes. When told that space travel is impossible, humans went to the moon. When told that faster-than-light travel is impossible, humans continue to search for loopholes in the laws of physics. This restless drive to transcend limitations isn't just about technology, it's about consciousness itself. Every time you learn something new, you expand the boundaries of what's possible for a human mind to comprehend. Every time you imagine a different future, you participate in the ongoing creation of reality. The implications go beyond individual growth. As a species, humans are becoming something new, a cosmic intelligence capable of manipulating matter and energy on astronomical scales. We've learned to harness nuclear fusion, detect gravitational waves, and observe the cosmic microwave background, radiation left over from the Big Bang. We're building quantum computers, artificial intelligence systems, and space telescopes that can see almost to the edge of the observable universe. If faster-than-light travel becomes possible, it will represent the culmination of this process, the moment when humans transcend the final physical limitation that confines us to a single world. But the journey toward that goal is already transforming us in ways that might be more important than the other destination. Every child who grows up learning about relativity and quantum mechanics develops a fundamentally different relationship with reality than previous generations. They understand that the world is stranger and more wonderful than common sense suggests. They know that the impossible often becomes inevitable given enough time and ingenuity. This is your legacy, regardless of your profession or personal circumstances. By seeking to understand faster-than-light travel, you've participated in humanity's greatest adventure, the quest to understand the nature of reality and push beyond the boundaries of what seems possible. The story of faster-than-light travel is ultimately the story of human consciousness awakening to its own cosmic significance. You are not just a collection of atoms temporarily arranged in human form. You are the universe developing self-awareness, exploring its own possibilities, and imagining futures that transcend present limitations. Whether faster-than-light travel proves possible or impossible, the quest to understand it has already succeeded in its most important goal: expanding human consciousness and revealing the extraordinary nature of ordinary existence. You live in a universe where particles can be entangled across galactic distances, where space itself can expand faster than light, and where consciousness can contemplate its own cosmic origins. In the end, the question, what happens if you travel faster than light, is really asking, what are the ultimate possibilities for consciousness in a universe that seems to have no limits? And the answer, regardless of the technical details, is that you are part of an ongoing cosmic story whose next chapters are being written by every human who dares to ask impossible questions and imagine extraordinary answers. The search for faster-than-light travel continues in laboratories and equations around the world. But it also continues in your mind every time you look up at the stars and wonder, what's possible? You are part of the solution to humanity's cosmic destiny, and that makes you truly extraordinary. Thank you for joining me on this mind-bending journey through the implications of faster-than-light travel. If this video has expanded your perspective on what's possible, please like and subscribe for more explorations of the impossible. And remember, in a universe where quantum entanglement is real, cosmic inflation occurred, and consciousness can contemplate infinity. The impossible might just be waiting for someone brave enough to make it real. The universe is vast, strange, and wonderful, and so are you for being curious enough to explore it. Keep questioning, keep wondering, and keep pushing the boundaries of what you think is possible. After all, you're made of star stuff, and the stars are calling you home.